Hello and welcome to the first of two lessons on the FP1 topic, complex numbers, in which we're going to look at the algebra of complex numbers. This video is quite fast and you will need to pause it, make notes and think about what's happening in order to fully understand the topic. We need complex numbers for the same reason we need all numbers, which is to solve equations. So basic equations like x minus 4 equals 3 can be solved within natural numbers, the most basic of numbers, whereas something like x add 4 equals 2 requires us to move into the integers, so negative numbers as well as positive numbers, but still whole. To solve 2x equals 7, we need to move out again into the rational numbers, which includes fractions, and to solve x squared equals 2, we have to invent real numbers, such as root 2. Similarly, to solve the equation x squared is minus 1, we have to invent the imaginary number I. In the same way that a real number might be made up of an integer part, 3, and a real algebraic part, root 2, a complex number is made up of a real part, so you might have 3, and an imaginary part, 4i, for example. If we're restricted to real numbers, then a quadratic equation with a negative discriminant has got no roots. Well, actually it's just got no real roots. Using complex numbers, we can now solve any quadratic equation using the quadratic formula. Even if that quadratic has a negative discriminant, we can always get two roots from the quadratic. So using this example, x squared minus 2x add 5 equals 0, and using the quadratic formula to solve this equation, we get x equals minus b plus or minus the square root of b squared minus 4ac all over 2a, which is 2 plus or minus the square root of 4 minus 20, which is minus 16, all over 2. So using what we know about complex numbers now, we can rewrite that minus 16 as the square root of 16 times the square root of minus 1. And that is 2 plus or minus 4i all over 2. So final answer, 1 plus or minus 2i. So those are the two sort of invisible roots that you can't see on a quadratic that looks like this. Now, you might have noticed that the quadratic, that the solutions have come out with the same real part, 1, and then one of them is plus 2i, and the other one is minus 2i. Now, this isn't a coincidence, and these are a special pair of numbers, complex numbers called complex conjugates, and the roots of a quadratic equation, if they're complex, will always come out as complex conjugates. Complex conjugates have got the same real part, but their imaginary part has the opposite sign, so from positive to negative and vice versa. So we've seen that complex roots of quadratic equations come out in complex conjugate pairs, but they can also be used to rationalise the denominator of a complex fraction. So for example, in the case that we've got here, if we multiply the top and bottom of this fraction by the complex conjugate of 2 plus I, which is 2 minus I, and then expand out the denominator, then you'll see that things start to cancel down nicely. So on the bottom we get 2 times 2, which is 4, we've got plus 2i, we've got minus 2i, and then we've got minus I squared. Now on the top, that's 6 minus 3i, and on the bottom we've got 4. The plus 2i and the minus 2i cancel out, they always will, that's the point. And we've got minus I squared, and I squared is defined to be minus 1. So altogether we've got 6 minus 3i over 4 plus 1, which is 5. So this has allowed us to write the complex number 3 over 2 plus I in its more simple form, 6/5 minus 3/5 I. The notation that we use for the complex conjugate is a little star. So if we have a complex number z equals a plus ib, then its complex conjugate is written z star, and that is a minus ib. If we're restricted to real numbers, then a cubic equation has either got one root, it's called a triple root, this one, it's the same root 3 times, or maybe a double root, same root twice and a single root, or 3 distinct single roots, like in this case, or possibly only one real root. Now that we can use complex numbers, we can see that all cubics have got 3 roots. In the case up here, we've got 1 real root down here, and then we've got 2 roots that are complex, and we can't see them, just like we can't see the roots of a quadratic, which has a negative discriminant, but we know that they're there. So this cubic in the top left has got 1 real root, and it's got 2 complex roots, and those complex roots are going to come out as complex conjugates, x plus iy and x minus iy. What I'd really like to be able to do in order to solve this cubic is to factorise it, so to be able to write it in the form x minus a, x minus b, x minus c, and then I could easily just say that x is a, x is b and x is c are the 3 solutions to the cubic. Now obviously, unlike with a quadratic, I can't do this with a cubic because I can't see what a and b and c must be, so I need to be given some information. So in this question I'm given the information that one of the solutions is 4 minus I. So with this information I can start to solve the equation. So for example, now I know what c is, it's 4 minus I. So that would tell me that one of these factors must have been x minus 4 minus I. But we know that complex solutions to equations come in conjugate pairs. So if one of the solutions is 4 minus I, then another one is 4 plus I. So that tells me another of the factors must have been 4 plus I. We don't know what a is yet, but we're certainly getting there. So let's shrink this down and have a look, see if we can see how much closer we are to solving the equation. So we know that we're trying to factorise, and we know that we can write the cubic in the form x minus a, x minus 4 plus I, x minus 4 minus I. So let's expand out those right-hand 2 brackets and see what we're dealing with. We're going to have x squared minus x lots of 4 plus I minus x lots of 4 minus I plus 4 minus I, 4 plus I. And this is where you're going to see lots of nice things happening with these complex conjugate pairs. For example, in this first expansion we've got minus 4x and minus 4x. But if you look at the complex part, we're going to get minus xi from here and plus xi from here. So the complex parts are going to cancel. Similarly, in the middle here, the plus 4i and the minus 4i are going to cancel. So lots of nice things happening because we've got these complex conjugate pairs. So altogether we get this, and then using the fact that I squared is minus 1, our expansion comes down to x squared minus 8x add 17. So let's expand this down and see how this helps us to solve the actual equation. So we're trying to solve this cubic by factorising, and we know that it can be written x minus a, we still don't know what a is, x squared minus 8x add 17. Now if we look at the front of this cubic 2x cubed and realise that this must come from these 2 terms being multiplied together, then we can see straight away that there absolutely must be a 2 in here, otherwise we can't make the 2x cubed. Similarly, at the other end we've got this 17, and this is going to come from the 17 multiplied by whatever we put here. So I can see that I need to make this, say, plus 1 in order to make the 17 come out correctly on the end. So it's really, really simple to get that final term. Just look at the beginning and ends of the original cubic and we can see what that final term must be. So this cubic factorises to 2x add 1, x squared minus 8x plus 17, and therefore in order for this to equal 0 we have to have x is minus a half, or x is 4 minus I, or x is 4 plus I. In this final example, I'm going to show you how to solve the equation x squared equals minus 3 plus 4i. Now clearly the answer is going to be a complex number, so what we do is we start by putting in x equals a plus ib, and we just want to find out what a and b are. A and b are going to be real numbers, and this is the notation for saying something is a real number. So if we substitute that into our equation, we have a plus ib squared equals minus 3 plus 4i, and expanding out on the left-hand side, a squared plus 2abi plus b squared I squared equals minus 3 plus 4i. But we know that I squared is minus 1, so on the left-hand side we've got a squared minus b squared plus 2abi equals minus 3 plus 4i. And now what we're going to do is we're going to equate real and imaginary parts, and what this means is we're going to have a look at how much of the left-hand side is real and compare it to the amount that is real on the left-hand side to get one equation, a squared minus b squared equals minus 3, and then we're going to have a look at how much is imaginary on the left-hand side and how much is imaginary on the right-hand side to get another equation, 2ab equals 4. And now what we need to do is to solve these simultaneous equations. So if we take the green equation first and rewrite that as b equals 2 over a, so that means that b squared is 4 over a squared, and then we can substitute that into the red equation. A squared minus 4 over a squared equals minus 3, and multiplying everything by a squared, that gives us a to the 4 minus 4 equals minus 3a squared, or a to the 4 add 3a squared minus 4 equals 0, which we can factorise. A squared add 4a squared minus 1, giving us the solutions a squared is minus 4, which is clearly impossible. Not if a is a real number, don't forget. We decided at the beginning what we're looking for here is the real part of the solution x equals a plus ib, so we can't have a being a complex number. We've also got a squared is 1, giving us a is plus or minus 1, and given that we know that b is 2 over a, that also gives us our b solutions, which is plus or minus 2. So the solutions to this equation, we found the a, we found the b, the solutions can be written as x equals plus or minus 1, plus or minus 2i, or slightly more pretty, plus or minus 1 plus 2i.